Okay, so let's start our lecture today. So, yeah, so let's start with the equation that I derived from last time. So, okay, so so last time. So we have that. So here we have the region 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. So yeah. So I get the formula in region 2, right? So in region 2, well, we have that. Yeah. So yeah, we have already have the n equal to 1 case, and then the sum is given by you take the sum from. So you have the n, right? So actually this n star what? So this is m. So this is like omega 1. So okay. So yeah. So this is our the omega 1 tilde, and then this is like omega 2 tilde. Okay. So so summation this n actually start at the bigger than k, right? So n star at k plus 1. Okay, so remember that minus omega 1 is equal to minus k times minus omega 2 plus s. Okay. So what we have is that okay, so let me just write this. So negative omega 2 to 1 plus n omega 2 tilde square. So this is equal to summation n from k plus 1 to infinity of so 4 n squared a2 squared plus a1 squared, and then this is negative 4 and a1 a2 minus 2i n squared a2 squared minus a1 squared. Okay. So now let's say so in the region 8 what we have is that we have n equal to 1, right? Yes. And then we have that so we have the sum is summation m equal to 1 to infinity of 1 over you have m omega 1 tilde plus omega 2 tilde squared. Okay, so I think last time I didn't simplify the formula here. So here I just take the simplified version. So for the coefficient on the denominator, so this is a complete square. So here I have a2 squared. So yeah, so a2 squared plus this m squared a1 squared. Okay. And yeah. Last time I think I showed that so initially there is initially it is like something negative and this one is squared, right? And there's like a some terms comes this guy with the negative sign, and then there's some constant like 16 like blah blah blah, and then it cancel out with the negative term that's inside here and make it positive. Okay. So then we also have like a 4m a1 a2 minus 2i. Let's say a2 square minus m square a1 square. Okay. Yeah. So. Right. So. So this is a equal to 1. Okay, let's think about like what happened in general, right? So, yeah, so this it seems that these sums are pretty nasty, isn't it? Yeah, so but here I think there are some common terms, right? So yeah, so this n star is k plus 1, and then this m star is 1. Okay, so let's try some more terms here. Okay, so okay, so then for arbitrary n, okay, so n arbitrary. So what do we have? What do we have here? So if n is arbitrary, what do we have right now? So if n is arbitrary, okay, so where does this m start? Okay, that's the question. That's right. So here for this n arbitrary, okay. So what I want is that I want to have this m omega 1 to be bigger than this omega 2, right? In order for a to lies in 8. So so what exactly do I need for this m times omega 1? Sorry. M times, okay, so need, so what I need is that this m times modulus of omega 1 must be bigger than equal to n times omega 2, right? Yeah, so Yeah, I don't think, wait, hold on 1 second. Okay, so, this M omega 1. Okay, I know that K plus 1 omega 2, right? So K plus 1 omega 2 is bigger than this 1 omega 1. Okay. But if you simply just multiply each side by K plus 1, okay. Do you count how many K plus 1 is inside this N? Okay, so maybe let's simply write it as this M is bigger than equal to N omega 2 modulus of omega 2 theta over modulus of omega 1 theta. Okay. Okay, so okay, so okay, so okay, so we will sum over it. Okay. Okay. So then the total sum is given by sum over all n, right? And then for each n, you sum from 1 m bigger than equal to. Okay, so I'll just yeah. So suppose that there is a so this is for each of the n, right? So there is a nearest integer that is bigger than this guy. Okay, bigger than or equal to this guy. Okay, so I'm just letting m to be the integer here. So m omega 2. M to be the integer that's bigger than or equal to this. The smallest integer that's bigger than or equal to this number. Okay. And then so this is equal to what? This is equal to okay, so now wait. I think that I need some computation because so this omega 2 it's not 1 anymore, right? So here I need some computation here. So let's see. So okay, so computation here. So if I have 1 over n omega 2 theta plus n omega 1 theta. Okay, so I'm letting
omega 1 tilde to be A1 plus IA1. Oops, so it should be minus. And then I'm letting omega 2 tilde to be equal to A2 plus IA2. Okay.
So this is equal to 1 over m of A1. Sorry, so this should be m omega 1, right? So
this is n omega 2. Okay.
Okay, so m times A1 plus IA1. Sorry, minus I and A1. Okay. Yeah, so and then plus n omega 2, so which is NA2 plus INA2. Okay. So this is equal to 1 over. Okay, so here first you have the real coefficient as NA1 plus NA2, right? And then so plus, let's subtract I from this one, NA2 minus NA1. Okay. And then, so this is equal to what? This is equal to, so first, so I square this one, I square the first one, I get NA1 squared plus 2mNA1 A2 plus n squared. Oh, sorry, it should be m squared. Okay, so n squared A2 squared. Okay, so then plus 2i times. Okay, so this is like a perfect square term, right? So let's see, n squared A2 squared minus m squared A1 squared. Okay. Okay. And then, so then the next term is minus this one squared, right? So I have an A2 minus an A1 squared. So when I expand it, what did I get? I'm getting n squared A2 squared minus 2 mN A1 A2 plus m squared A1 squared. Okay. So this is cancelled with that. This is cancelled with that. And then, so this is being added. Okay. 4mN A1 A2. Okay. And then plus, okay. So now I multiply by the conjugates. Okay. So which is equal to, so on the top it is more 4mN A1 A2 minus 2i n squared A2 squared minus m squared A1 squared. Okay. And then for the denominator, okay. So so this is Okay, so if I put a conjugate here, so what I get is that, yeah, so this is just yeah, so this is not part of it, okay, so, yeah. Okay, so, and then, yeah, so 16, okay, so m square, n square, n1 square, a2 square, and then it should be a plus, right? Okay, n square, a2 square, minus n square, a1 square. Okay, so now, okay, so this, so yeah, so when you, oh shoot, so there should be a square, yeah. So again, if you expand this out, you will get a net minus 2m square, n square, a1 square, a2 square term. Times 4, which is 8. So this will be cancelled out with 8 copies of that guy. And then once that is out 8 copies. So yeah, so we can safely write just make it a plus here. Okay. Okay, so yeah. So let's copy it down here. Okay. So for n squared a2 squared plus m squared a1 squared. Okay. Okay, so let's also write it as the general formula for this one, right? So for this one, what I get is that so for m equal to 1, okay, so initially it should be m equals, so this is minus m, right? So if I put a negative sign here, then what will it change? Okay, so okay, so so here I add a negative sign in front of this m times omega 1, right? So what I have should be, this should be minus, this should be plus, right? But omega and tilde, okay. If you multiply by m, there will be ma1 minus ima, okay. So minus, okay. Okay, so, and then this guy will be negative here, right? Because, yeah, this will be negative. And then this ima becomes positive, okay. Okay, so we'll square it, right? So the first term, so this won't change, okay. So and then this will become minus, okay, and then this won't change, and then plus 2i, so yeah, so again this won't change, okay. Yeah, and then this guy, yeah, so this will be plus here, okay. So eventually it will become minus, okay, yeah. And then we multiply by the conjugates. So multiply by the conjugates is the same thing, right? Okay. And then what about the bottom? So when you multiply by the conjugates, so it will be 16, right? Yeah, so it will be same thing as 16 m square, n square, a1 square, a2 square, okay. And then if you multiply by the conjugates, yeah, so then this the last term becomes -4, +4, right? And then with a negative sign here, okay. And then you also get this cancellation, okay. Let me think carefully. So if you square it, yeah, positive, yeah, okay. So you will get, yeah, you will get the same thing here, okay. Yeah, I think it makes sense. So, okay. So for m equal to z plus, okay. Yeah. So another question is that where does this n stop, right? So I want this n to be okay. So, or what I need is that, okay. I need is that this n times the modulus of omega 2
modulus of omega 2 must be bigger than or equal to this m times modulus of omega 1. Okay.
So namely, what I have is that we have the total sum yeah, so by the way, it's not for it is for any m, so we are summing over this m, okay. So sum over from 1 to infinity. Okay. And then we got this n must be, so n is like the, yeah, again it's the closest integer to this guy. Yeah, so m omega 1 over omega 2 to the of okay, so -4 mn a1 a2 minus 2i n squared a2 squared minus m squared a1 squared. Okay. And then over this 4 n squared a2 squared plus m squared a1 squared squared. Okay, so the denominator is exactly the same. Okay. So, and for the numerator, right? So you can see that this term sort of cancel out. Okay, sort of cancel out. Okay. So what about the imaginary term? Wait. Are they the same thing? It must be. Oh, okay. I think I may make some mistake in my computation somewhere. So. Let me check my notes here. Yeah, so the imaginary terms. It's bothering me right now. So, it seems that they are the same for the imaginary terms. why they should be the same for the imaginary terms. Okay, so yeah, so okay, so I think I find a so actually can I can I switch the term can I switch the sums? Yeah, so can I actually like Fubini yeah, so can I switch so for each fixed m, is this gonna converge? So if you fix the m here, so I think so because so if you fix the m, right? So both the real part and the imaginary part will converge, right? Yes. So and then if you sum over this m, wait. If you're that's so complicated. Wait, hold on. So if you sum over this m, so for each n you are getting this fixed number. Then you are summing over this m. So what do you get? Okay, so yeah, sorry, I have to stop right now. So I'll try to do the analysis here next time.